I can do post-production.
Okay.
All right. I want to introduce Dr. Jeb Flemming from 3D Glass Solutions. He's been kind enough to take time off of his extremely busy schedule to talk to you guys. So I want you to pay attention, write things down. We got an assignment associated with this. And I'm going to read everything, make sure you're paying attention. And something unique in his presentation that's useful to career planning and engineering. We're going to try to record this if everything goes well, which it has so far. We'll have it on YouTube. You can watch it again later. Take lots of notes and really ask a lot of questions. You know, don't be sleeping. Okay? All right. Without any further ado.
All right. Well, thanks. Well, what I kind of put together is a 2-point presentation. Kind of give you a little background on my company. I have a local business here in Albuquerque. We service customers all over the world. I'll kind of talk you through a little bit of the technology. I'll go through a little bit of my background, and then since you guys are in the Introduction to Engineering class, I put together some slides on why you should be an engineer. Personal experience as well as fact-based decision experience, and I'll kind of go through that as well. So my company name is 3D Glass Solutions, abbreviated 3DGS. Who are we? So we were created to service the IC community, integrated circuit community, for a number of applications, and we do this by selling our glass to companies and letting them process our material. It's like it's a glass material, just like you would find in like a silicon type of approach, except for it's just glass. And what it is that we have the ability to do through holes in glass very quickly, very precisely, and very efficiently. If you look at traditional glass processing techniques, people will do just a drilling or a laser ablation of very small holes. And we do actually a wet etch process. I can etch 25 or 50 wafers simultaneously, where comparatively a laser will do 1 wafer at a time. What that means at the end of the day for our customers is very economical and cheap manufacturing. You know, everything that you look at with respect to your cell phone, the bottom dollar is what matters the most. It's not how cool it is, it's not how fast it is. Those things are drivers, don't get me wrong. But at the end of the day, whether or not it makes it in your phone or not is cost. So making through holes in a number of substrates is pretty much the basis of all communication. If you look at your cell phone, which I don't know where mine is, probably the car, but which is probably a good thing for me. If you look at your cell phone, I mean, there's a chip in there, it's a computer chip, you know, produced by Qualcomm. That chip may have 10,000 ins and outs or IOs. You got to get 2 of those to your home button. So they go from that, you know, that chip that's the size of your pinky nail to the electronics to your home button has to fan out, and that's what the material that we provide to our customers. So I'll pass around some examples, but you know, this wafer right here has about 300,000 holes on it, and it takes me about 30 minutes to process it. So compare that to something like a laser would take about 4 hours, but they can do 1 wafer at a time, and I can do 25. So I'll pass around several examples.
How is that done? Is that masked like in lithography first to get those holes precisely set up?
I'll get there, yeah. I'll explain a little bit, yeah. With my business here in town, we do pretty much 3 stages of manufacturing for our customers. We'll sit down, we'll design with them. We'll look at what they want to produce and take that into kind of a design laid out in a mask, a lithography mask. We'll then go ahead and build a prototype. And then in some cases, we'll move to a production model internally, where if the production volumes are very low, which we can handle domestically, then that's great. If there is an opportunity where the production volumes are very high, then we move those offshore to facilities that exist that can handle, you know, hundreds of millions of parts per year. We have some customers that are talking up to 2 billion parts per year. While I like manufacturing, you know, our little facility will not handle that. So we do kind of partner with other manufacturing companies. Here's another example of through holes as well. Gives you a little more, there's some pattern to it. So the way our glass works, if you think about, again, traditionally laser ablation or drilling, but our glass is a little bit different. We take a material the raw material, we put a lithography mask directly on top of that, and then we expose that to ultraviolet light. During the exposure step, a redox takes place, and something gives up an electron and something receives it. And in that state, it still looks like glass. But when I put it through an oven, what happens is the areas that I once exposed get converted into a ceramic. So it's actually, in that case, it would be considered a glass ceramic. So this is an example of my company's logo in a 4-inch wafer. And what you see, the brown here, that's the ceramic. It actually goes all the way through the material. So it's not on the surface, it goes all the way through it. And what happens is that this ceramic is 60 times more soluble than the surrounding glass. And so we leverage those differences in how it etches to get our features. I'll show some examples of that. So. I mentioned kind of the, how our material works a little bit in cell phones, but this is kind of a cartoon approach. So you have your, your motherboard, you have your circuitry kind of on the top, and what you have to do is you have to take all the integrated circuit, electronics, and fan them out to the motherboard. And we do that with our material. So imagine that this layer right here would be kind of our material in the grand scheme of things. In cell phones, we find that our material is useful in things like we're doing inductors, we're doing power amplifiers, we're doing just a number of integrated components. I mean, there's a lot more there. I can't really explain a whole lot too much into it, but there's a lot of opportunity we work with. We have about 9 different customers in cell phone components, and they're all geared towards electronic packaging. So some of our industries: portable consumer electronics. We also do large electronic applications. You guys might be familiar with the newer cars having radar for detection of curbs, vehicles in front of you, vehicles behind you. Those are becoming more and more prevalent, and we're doing some work with some customers geared towards that. The idea is more efficient radar, better detection distances, and things like that. We also do large electronic applications with respect to display in some cases, and then also satellite communications. And we do a lot in avionics, optoelectronics. That's the blending of electronic systems with optical elements. So you might think of a very small chip with a lens on it. Those are things that we're doing with customers. And we do a lot with infrastructure, things like wireless antennas, Wi-Fi boards, and things like that. So it's a pretty diverse marketplace we work in, which leads to, with one major design guy at the top, a lot of diversity in my time. So a couple examples of what we're doing and the size that we can do it. So these little guys right here, I don't have an example of these, but these are pillars. They're 300 microns in diameter, and they're about 500 microns tall. To give you guys an understanding, I think you guys probably have a good sense of scale, but your human hair is about 100 microns in diameter. So we can do very precise elements here. We do kind of undercutting. I'll show some other kind of cooler looking pictures of what's called a high-Q, high-quality architecture in electronics. And then we also do copper plating. So these holes right here are 60 microns in diameter. So that's 12 red blood cells wide, and they're all filled with copper. That's what the shiny material is. We do microfluidics, high-temperature electronic boards, and then some other custom 3D fab on the bottom right there. These pillars, kind of give you an idea, these pillars are 15 microns in diameter at the tip, and they're about 800 microns tall. So very small features, which you just really can't do in any other glass material. Very, very small holes. These holes right here are 14 microns. They're 17 microns apart. So 3 red blood cells won't even fit inside that hole. One of the things that matters in this industry as it relates to electronics is what your through-hole cross-section looks like, and that's what ours looks like. Very nice. They call it anisotropic profile, very straight sidewalls. And the reason why they want straight sidewalls is because you can pack more holes in there. The more holes, the better off everybody will be as far as processing power, frequency, how much data you can transmit, things along those lines. Just some other kind of cool pictures of some stuff. These are copper pillars that we've etched down and have the copper sticking up. Just so some fun stuff. This wafer right here kind of it's a 4-inch wafer. and it's got a number of 1 centimeter by 1 centimeter squares, and within each square there's 25,000 through holes. So this whole thing has 2 million holes in it, and it took me about 25 minutes to make it. So, and again, from a cost perspective, I can do 50 of these simultaneously. So I'll pass that around as well. I have a couple other examples here. This shows kind of, if you have good eyes and you have the right light, you can see some of the, these are individual circuits that we've built for a particular customer. If you got really good eyes, it looks really cool. With your regular human eyes, it won't work real, doesn't look that, that fancy, but then these are also some other images here. These will make a lot more sense, but we can do very fine features like watch gears, and I'll pass those around as well. And let's see if I have anything else as far as examples. That's pretty much all of it. I got a couple others, but that's good. So we can get real crazy in our work. I'm an engineer, chemical engineer. I'm not an electrical engineer. So things can get real crazy real quick, but this is kind of an example of the things that we can do with our material that we do for our customers. If you look at this, so this line right here is about 100 microns wide for scale. These guys right here are about 20 microns in width, about 80 microns in length. These are all copper-filled solid slugs of material, and then this is a copper line on top of our glass. And what we've done is this is a high-quality design feature, and we've etched down the surface so that these copper fields are kind of like an EMI shielding material. So if you think of like a Faraday cage, if you look at if you ever break your phone and look inside, you'll see a lot of metal all over the place, and that's A, to protect you from the radiation, but B, to protect the phone from external radiation. So that's called EMI shielding, and that's what these little guys do here. And you can also see that by etching the field, we've also undercut some features over here for this resonator, which is an antenna. This is all geared towards 180 gigahertz, which may not mean a whole lot for you guys, but it's really geared towards long distance communication. A little bit more background on some technology. For those of you, so why our material? This gets into a little bit of the minutia, but kind of gives you some more information. Our material is used in radio frequency packaging for a number of reasons, but basically it overcomes the limitations associated with traditional materials. Traditional materials include alumina, which is aluminum oxide, and then it also includes also things like the PCB board, like FR4. So you look inside your computer, you see all the green boards. Those are all laminates. They actually physically glass sheets that are laminated together with a resin. Those are called FR4, fire retardant recipe number 4. And we work with our customers to move beyond those materials simply due to we can do smaller features. We can do more through holes, smaller through holes, get chips to be smaller altogether, which drives down cost as well. So that's kind of the main thing that we do for a lot of our customers. There's some technical information related to dielectric constant and loss tangent, which is probably a little bit early for you guys, but when you're in the cell phone industry, that is the main driver. Those are the two things that matter to everybody. What's your DK and your loss tan? That's what you'll get a lot. That's what I get a lot of questions on. So I think that's kind of on that slide. We also do other application spaces here with respect to, let's see. We also do pure ceramic parts. Mentioned it's a glass and a ceramic. So the ceramic has different properties than the glass does. You can leverage those depending upon your application. The ceramic is opaque. In the visible, it's also transparent in the IR, which has some unique characteristics. And we also do a lot of pin nests for burn-in sockets. So at the end of the day, every chip that's produced on the planet has to be tested before it gets put into a cell phone. So they have these little guys, these computers and the robots that kind of do all this manually. And that part that does that manually is a pin nest for the test socket. We do a lot of optoelectronics, as I mentioned, photodetectors and VCSELs integrate onto electronic packaging. So that's kind of the high level. I think I got one more slide on what we can do. Here's some other kind of cool pictures here with respect to metallization, surface metallization. This is copper. This is 10 microns thick of copper. These little black dots are the holes. And then here's some 9-micron diameter holes that are spaced 20 microns apart. So just some other kind of nice pictures. So to kind of go over a little bit about how I got to here where I am today. Well, before I do that, is there any questions on the material I went over? It's probably some high level, probably some low level, but I didn't
catch what you had said earlier. If it was the mask portion or the exposed portion that became ceramic.
Okay, so that's a good question. So it's a positive tone material. So the areas that we expose get converted to the ceramic.
Okay.
Yeah.
And could you elaborate a little bit on the material properties that allows them?
Yeah, the nuts and bolts of it are there's a whole lot of chemistry, but basically you bring in light at 310 nanometers. Okay, at 310 nanometers, there's a molecule that gets hit with the energy, and it just says, "I no longer need this electron." Okay, and there's another molecule right next to it that says, "I'll take it," and that's the redox part that happens there. Now what happens is that I then bake it, and I do a two-step bake, where the first bake, the guy that took the electron, he gathers up with all of his other buddies that took electrons, and they form little tiny nanoclusters of this was a precipitated metal. And then there's a second bake, which we take up to a little bit higher temperature, and all the other ceramic forming compounds, these are lithium compounds, form around these nanoclusters. So that's how that all kind of takes place. And what it is you're trying to make nanoclusters of ceramic that are small, uniform in size, and you want them to be, I guess those are the two main things, because what happens is you etch into an HF acid. We use hydrofluoric acid. Most glass etching is done at 50%. We use 4%. But the main thing is that as you etch into the ceramic areas, those little tiny crystals are about 70 nanometers in size. Tiny crystals. You don't etch one layer at a time. You actually etch the grain boundary. They pop off, go into solution. They dissolve later. But the whole game that we play is trying to get as much reactants into those little areas to etch them, so they can pop off and make make more room for the next layer of ceramic clusters. Did I answer your question? Okay.
And the whole process happens?
The etching, we will etch through, we etch double-sided a lot of stuff, so like a 500 micron thick wafer, so 0.5 millimeter thick wafer, we'll etch 1 to 1 million holes in about 15 minutes. Yeah. That's really good. It is. And we can hold it to diameters of plus or minus like 1 micron. I've done 28 micron diameter holes, plus or minus 1 micron. I just did some larger holes for alignment purposes. They were 750 microns, plus or minus 2 microns on that. So, and that just makes good translation to electronic modeling.
So what makes this a better process than, say, silicon is the fact that ceramic can get etched easier and faster than silicon itself, or?
Yeah, so if you look at like this picture right here, on the top right, so everything's focused on having these holes filled with metal. Okay, on the top I'll have the chip that goes on top of that, and I'll have the metal that goes through the chip and then fanned out. So the chip is really there for structural integrity, among other things, but that's one of the primary purposes. But it's also there to house this solid copper. So what kind of a material is silicon? Semiconductor, right. So it means it partially conducts. So when you have two very closely related or closely aligned electrical conductions, you do not want them to communicate to each other. So by having a dielectric like glass, you avoid that. So that's the main reason for glass as well. So, you know, you may be able to have these two circles copper filled on silicon, but they might need to be 4 times the distance apart. And if I can use a dielectric and make them 4 times closer, then my chip can be, you know, 4 times smaller. And if you think about it this way, let me grab one of these 6-inch wafers here. So like on this wafer, if I can reduce my chip size by 66%, you know, what that translates into is I can produce almost 3 times more chips on here. Same area, but 3 times more chips. So that means my cost at the end of the day is actually 1/3 or 2/3 less. So again, it goes to the cost driver. So that's kind of the main reason why people want to move to glass.
I was handling one of those wafers when you pass along the one with the gears,
Mm-hmm.
the little box. What do they use those for?
Nothing right now. It's just show and tell. I mean, when I show someone, you know, like a wafer like this, and go, "Wow, look at the cool holes," you know, people look at it and go, "Yeah, thanks, dude." You know, there's no real-world practical experience, you know, so that you can put your hands on. But gears, watch gears, people kind of get a good understanding of that. It just shows that you can do really small features, very precise alignments, and I just kind of catted those up real quickly and then made them.
Yeah, it's just better than the silicon, then I take it, since you get the clean.
Yeah, so you can get very,
Compared to silicon.
yeah, you can get very, oops, wrong way, anisotropic etch rates or profiles in silicon. It's a process called Bosch. It was developed by Bosch out of Germany. It's actually a very elegant process. It's probably what, in early 80s, mid 80s?
Yeah, something like that.
The difficulty with it, and they have a tool over at the MTTC that does it. The difficulty is that the tools cost, you know, on the very, very low end, I mean, baseline models can cost up to $1 million, whereas production tools that can, you know, push things in and out real quick can cost, you know, tens of millions. So, I mean, to do something like with us, I can do, my entire capital for my entire business was $300,000. So I could buy 10 lines for one tool, possibly. And that just goes to lower barriers to entry in the marketplace. So if I say to, you know, Foundry A in Taiwan or Foundry B in San Diego, and I say, look, you know, you will have to buy this piece of equipment, they're like, oh gosh, you know, capital expense. We were just talking about this, and I go, no, it's like $100,000. They're like, oh well, shoot, I can handle that. You know, that's not. Yeah, exactly. You know, because today's semiconductor equipment, I mean, when you look at like the aligners for Intel, what they're doing with their computer chips, just the aligner, the part that takes the mask and lines up the wafer below it, $30 million for one tool. It's a stepper. Yeah, EVG. Yeah. So the big one they use is ASML. Yeah. And like I said, one tool, $30 million. So my exposure tool cost like 15 grand. But we're talking different scales. I mean, they're talking, you know, nanometers. My smallest features are, you know, 8, 9 microns in diameter. So, okay. Any other questions on kind of the technology? Yeah.
Has it made its way into this everyday use?
We have a number of applications that are moving towards that. You know, I mentioned cell phone parts. We also do work with DNA diagnostic test kits, where we're moving that in there. Number of other kind of life science research tools. Everyday use, though, not quite yet. I mean, a lot of people are gearing towards that, though. I mean, as far as, you know, the adoption of material and prototyping, things like that. So, but it's very diverse. I mean, it's. I showed that slide. It's from cell phones to UAVs to, you know, point-of-care diagnostics. So.
Is the intellectual properties that make, you know, that make your company successful? Is that the material itself, or is it the processing of the material?
All of the above.
All of it.
Yeah. So we actually have. I mean, when you start your own business, there's a number of ways that you can be valued. One of the most important ways you can be valued, obviously, is your intellectual property. Intellectual property can come in many forms: trademarks, patents, or trade secrets. With respect to patents, we actually have patents granted on the material composition. We also have patents granted on how you process the material, the exposed bake edge. And then we also have patents that are geared towards the structure you make. Putting holes in glass ceramics in general, copper filling them, putting in holes and doing an etch back to provide you with some etch relief on things, those types of high Q structures. Those are all kind of application space that is patented as well. At the end of the day, I mean, that's kind of one of the major things that we take a lot of value in. Okay, all right. So I thought I'd kind of, I'm not quite to the other half yet, but the other half I'll get to in a minute, but kind of give you some of my background, because not too long ago, well, depends how you look at time, but about a decade ago or a little bit longer, I was in your same shoes, you know, so being a student and going, okay, what kind of engineering degree do I want to get, and why do I want to get it, and what's my motivation? You know, so I graduated from New Mexico Tech with an undergrad in chemical engineering. Started working off at Sandia as a summer intern that turned into a full-time intern that turned into a member of the technical staff, and which I ended up getting a fellowship through Sandia as well to get my my master's degree. I actually was enrolled in the PhD program. I'm not a PhD. You called me doctor before.
Well,
you can refer to me as master if that's okay. No, just kidding.
you know, better work than a PhD, so it doesn't.
Well, I did effectively kind of drop out of the PhD program and got my MBA instead. And I don't mean to disparage the PhD program at all for anything. I think there's a lot of value in getting that. For me personally, I felt that a business degree was more kind of up my alley. And sure enough, a year after I completed my MBA, five years in night school, I started my own business. So it was pretty timely, I guess. And then I left in 2008, left Sandia, and I've been working with this business and on this business since I started it. So that's kind of my main path. To give you a little more background on where I started, I started off as a biology major. I was about 3/4 of the way done with my biology degree at New Mexico Tech, and my cousin, who was going to school with me at the same time, kind of sat me aside, took me to the library, and showed me the earnings tables for biologists. As a brand new biologist, what could you expect? And I think at the time it was like with a bachelor's degree, you would get $31,000 a year, you know, out of college. And I was like, yeah, that's cool, you know. Coming from a grocery store as a summer job for high school, I thought that was great. And then he showed me, look, what you should look at is the engineering. And I'll show some comparisons here. You know, Chem E, starting salary, $78,000. And I was like, wow, that's a lot different. That's 3 times or 2 times the cost, and a different kind of quality of life that you could look at. And so I switched my majors the next day. That was pretty simple, you know. So kind of with that, I'll kind of go into, you know, some of my advice to, you know, to you guys. You can take it for what it's worth. But it's kind of some of my thoughts on higher education and what, you know, some questions that might be pertinent to what you're thinking about or what you're looking at in the future. So my thoughts on higher education. So certainly there's outliers to not getting a college degree. Bill Gates, you know, Michael Dell, there's lots of Zuckerberg, a whole bunch of other people don't have any college degrees. They may have a year or 2 of college education, but they don't have any degrees. But for the majority of the people, the middle of the bell curve, a college education is what I believe is one of the most important things that you can get to be successful. I think a bachelor's degree is good, but I think at a minimum a master's degree is better. And again, that's just my personal preference. And I am indifferent to a PhD, meaning that if you don't want to get a PhD, it's the same value for me as getting one. Like I said, my personal path was to get an MBA. And to be honest, I use the MBA probably 50% of my time now. You know, being a business owner, I use it a lot more than I did 2 years ago, and I certainly use it a lot more than when I started the company. And I think that's kind of probably a natural trend in any engineering, that the older you get and the more senior you get at any particular company, the business side becomes more important for you to adopt and use the right language. People will come to you on yields. Why yields? Because it can come down to revenue, profit, margin, things like that. Those are going to be all things that at the end of the day make a difference to the business, which of course will pay your paycheck. So I also look at college, and in particular engineering, not only as an opportunity to learn, but as an opportunity to learn differently. And what that different decision making comes down to is it's data driven. You know, a lot of times when you look at decision makers, there are several different types of people, personalities, people who, you know, make a decision on a whim without a lot of thinking, and that's fine, maybe fine for a particular situation. But in engineering and a lot of factors in life, getting a car, buying a mortgage, at some point you'll have to have data to support why you're making a sound and educated decision. And I think that's what engineering really taught me, is to be data driven. And then I already covered it, but I said that, but ignore that. So, you know, the question that when I was faced with that table of first year salaries that I looked at was, you know, what's going to motivate me? And I'd ask you guys the same question: what's going to motivate you? Is it security for you and your family that you may have in 20 years? Is it going to be, you know, the diversity of work? You know, I'm a chemical engineer. I do material science. I do electrical engineering. I do mechanical engineering. I'm all over the place. And I think that is enabled because of the diversity I had in my education. So I think that's really important, at least for me it is. But flexibility, you know, I can go anywhere in the nation and have a job. You know, oil and gas, which is truly what chemical engineers do, you're not necessarily allowed that same type of diversity in location, perhaps. You're mainly going to be, you know, the Balkan Shale deposits, or, you know, North Slope of Alaska, or really predominantly oil and gas fields, Texas, New Mexico, and Gulf of Mexico. But you really might not have a good job if you wanted to go to Oregon or something like that, which, you know, some degrees allow you to have that flexibility. Certainly work-life balance is going to be important. And then, you know, is it easy for you? I mean, at the end of the day, I hated being a chemical engineer. I mean, getting a degree, because I was horrible at it. It was so much easier to get me a biology degree. I didn't even have to study. But, so this was definitely not my motivation. But at the end of the day, obviously, as I mentioned in my story, you know, salary, and which could be different than cash money. I know people who get into high degrees, you know, master's level of computer programming, and take a job for $30,000 a year with a whole lot of stock options. I mean, they're not in it for the salary, but they're in it for the payday at the end of the, you know, the IPO. So the question to you is, you know, what motivates you guys independently? And I think that the best way to look at what motivates you, you can look at from a short term, or you can look at from a long term. And I encourage you to look at from what's it look like in 20 years. Because in 20 years, things will be different for you. I mean, some of you may already have family and kids, but in 20 years, if you don't, you probably will. And at that time, it's not taking care of yourself, it's taking care of your family. So the question becomes is, you know, in 20 years, does U.S. manufacturing rebound? Right now, we're 70% of our economy is services. Does manufacturing rebound? I think it is. I mean, we're a good example of that. But I also see it in other places as well. So manufacturing rebounds, then what you'll see is more and more engineering necessity. But right now, I'm sure as you know, I mean, the engineer numbers of graduating engineers just are not meeting up with demand at this point. So, you know, does service work decrease? What would oil and gas look like in 20 years? You know, Tesla is a big opportunity for a divergent thinking. And if you look at Tesla, does that grow into a bigger vehicle opportunity besides, you know, the 3,000 cars they sell a quarter now? You know, GM sold, you know, 2 million cars a quarter. So, but is oil and gas still prevalent? I think it obviously it should be and it will be, but it might look less. You know, what does those domestic look like versus global trends? You know, if I had known that computer science would have been as big as it is today, I probably would have gotten a computer science degree. Just simply because I was following the money. And today, you know, CS degrees are one of the highest paying, certainly on the cash out side of things. Other things to kind of think about is, you know, what's quality of life? You know, working 9 to 5, making, you know, a whole lot of money and having the opportunity to spend it and enjoy time with your family. You know, on the flip side, will things get worse? If you know, as you go into engineering, you'll learn the second law of thermodynamics. Everything gets worse to some degree. It's a little more technical than that, but that's my interpretation of it. Says the chemical engineer, you should know all that. But and then what will the technology do to the labor markets? That's a big unknown. You know, one thing I've just started looking at. You know, how will technology help or hurt labor markets? And let me just take this. So one of the things that I look at is, or I have been looking at, is technological unemployment. A lot of people, you know, are kind of, I think this is kind of a buzzword I've heard in the last 2 or 3 months. You know, what it basically means is that, you know, there are factors that are non-human, such as robots and software, that are performing what they call these middle-skilled work. And what that does at the end of the day is it says, well, we used to have a hierarchy of work function between low, middle, and high, but if the middle-skilled work is eroding due to automated services, that's going to make the difference between the low and the high end even greater. So if that translates, and that's a big if, you know, people are saying that, you know, it could drive unemployment between 20 and 40%. Is that realistic? I don't know, but let's say it's 5. If you erode 5% of that middle work area, which side of that curve do you want to be on? You want to be on the upper side. So those are things that, you know, from your generation that you may want to consider. If again, who knows if it happens? I think it's already happening, but to what degree, I think is up for debate. There's a lot of good resources out there. The Onrushing Wave, which is an article on The Economist, the Race Against the Machine, which is based upon an article written by these 2 professors at MIT. And then the new one that's kind of been making the rounds lately is by Jared Cohen and Eric Schmidt from Google, The New Digital Age. They just made a lot of the kind of talk shows recently. So why engineering and all this? These motivational elements, because you'll learn to think differently. As I mentioned, it's data driven, but this will permeate through everything in your life. You know, very simplistically, you look at, you know, our city, you know, the guys that typically live up along the hills, there are a lot of engineers up there. They can afford that because they have the right education. Now, I've also met a lot of engineers that really flame out, don't get me wrong. Sometimes I meet a lot of engineers, especially when you go to New Mexico Tech. But at the end of the day, I mean, you'll typically almost always have a job. I mean, that's, I'll show some employment metrics here. And, you know, in this economy, that's important. You know, will it get better? Maybe. Has it gotten better? Not really. You know, I think this is a pretty long recession. So certainly, and then certainly engineering allows you to have more income. And, you know, money doesn't buy everything. It can buy happiness, doesn't always, but really what money can buy is stability, and stability leads to, you know, having a better quality of life. So some statistics, data-driven, degree versus no degree. Here's the unemployment rates. Pretty different. And this is generic. It doesn't matter what kind of degree you have in this chart. Bureau of Labor Statistics. So yeah, if you have a degree, you know, we hear about the unemployment rate being at, you know, 8, 9%, 10 at its max in about 2010. But if you had a degree, it never peaked above 5%. You look at college majors with the lowest unemployment rate, medical technology technician, 1.4% unemployment. That's pretty darn low. I bet you that 1.4 don't even want to work. Nursing, 2.2. A couple arrows here. Mechanical engineering, 3.8. Civil, 4.9. And electrical at 5. But really low unemployment rates. I'm going to bet that chemi is not on here only because they didn't find any chemis that were unemployed. Here's the chart that got me out of the biology degree. But this is the top 20 best paying college degrees. I think it's 11. Is that 5? 13. 13 of the top 20 are all engineers. Now this is mid-career. So at the time I was at school, petroleum engineer was also the highest. I just didn't think I wanted to go down that road too much, but chemi, because it had more diversity and opportunity, I definitely took that one. But you know, petroleum 155, chemi 109, aerospace 102, computer 101, biomedical, which UNM offers, 97, a little bit above 97, mechanical 94.5, industrial engineering 93, civil 90. I mean, real high salaries. Mid-career, you probably look at mid-career, it's 15 years into your career. But that's a lot of stability in your life. It can really, kind of keep things normal. A couple other things. I'm almost done here, but earnings of unemployed versus degree attended, or degree attained. So you look at associate's degree. So this is the unemployment rate over here as of 2013, and then this is the degree level. But just look at the trajectory of basically less than high school to a PhD. I mean, if you have a PhD, your unemployment rate is 2.2%. I mean, again, I bet you that 2.2% don't even want to work. That'd be, be my guess. But median weekly earnings, on an average, you can see a little bit of a trend there. Certainly see a trend up to, your master's level, and then you have above a master, you get the doctoral, which is also greater than that master's. But you have a professional degree, which I had a hard time figuring out how they define professional degree. They didn't really. That would probably make sense, yeah. Okay, so there you go. And I'll leave you, I think, with just one more thought here. So if you make more than $10,000, you earn more than 24% of America. If you take that out, you make more than 30, you make more than half of America. And if you make 100, you make more than 93% of Americans. And if you make more than 250, you're officially the 1%. Some other interesting things, 894 people earn more than 20 million in the United States, and they totally bring in 37 billion. So just some interesting statistics, that puts it in perspective. Not everybody makes 100,000 or has the opportunity to make $100,000 a year, but engineers do. So that's what I put together.
Good.
Any questions? Yeah.
Have you thought about biology maybe in a hobby type capacity?
I'm so busy right now that the word hobby makes me sick.
Where's the balance of that?
I got work and kids, and I got 3 kids, and they take up all my hobby time.
I was thinking about it because the chemical engineering program at UNM offers a concentration in bioengineering. So I was wondering if you ever looked down that path.
So my old professor at UNM started that program. I think it's a great program. So part of the reason why I also chose chemi over petroleum, a lot of chemis will move into petroleum. It's a natural trend. You're doing fraction towers, you're doing a number of control theories, power plant. I mean, chemis build power plants. I mean, that's refineries and things like that. But part of what I also looked at with chemi was the diversity of the education. Petroleum at that time, where I was going to school, was very narrowly focused on petroleum. You look at, At that time, a CO2 injection was the main thing. So they had injection wells and a bunch of other stuff. Whereas Chem E, I had to have a year of material science. I had to have a year of physics. I had to have a year of chemistry. I had to have a year of biology. I had to have a year of mechanics. I had to have a year of double E. I mean, so there's a lot more diversity in that, and I felt that that was important. So where I'm going with this is that the fact that UNM has a program that is diversely proportional, where you can get a Chem E degree, you can go and build a power plant if you want, but you can also go over here and do biomedical research. It's tremendous. It's a great opportunity because you won't find that in other degrees.
Can you talk a little bit about the process for the Sandia Lab internship? It's something I've always heard about, and it sounds really interesting.
Yeah, I probably had a little bit more of a unique one. I've had 2 summer jobs. The first summer job I got hired because it was basketball, and I didn't show up to the interview because I was wearing my jersey. I did show up. I handed my business card, which was a piece of paper with my name and number on it, and handed it to him and said, I need to talk to you, and then I ran off to the basketball game. He hired me. I got real lucky, to put it simply there. But at Chem E, or at Sandia National Labs, it was, you know, I knew someone who had a summer internship job there, and her advisor was looking for someone to replace her, and she recommended me. I went through the formal interview process, but I found it to be very beneficial. Sandia is one of those jobs that I got to utilize my diverse education. I did things from, you know, from neutron generators to a lot of life science stuff. I did a lot of chemical and biological detection engineering, systems engineering. So looking at like the big thing at that time was anthrax. So building sensors for anthrax, building sensors for chemical weapons as well. It was mostly focused on microfab work, but it was all over the place. Satellite optics, just, you know, CO2 monitoring. So I liked that part about it. I mean, that's why I got my degree in the first place, and it was a natural extension of what I could do. So yeah, I mean, it was. They have a formal process nowadays that you can put in. I think the big thing, they have these, you know, massively paralleled, you know, approaches to weeding out interns via resume, and that's not necessarily the greatest thing because if you don't use the right buzzwords in the resume, you don't get picked up. But I know a lot of guys that were at Sandia that would, you know, just randomly take a phone call from an individual at a school and end up hiring that person as an intern. I knew quite a few people who did that. So that's the way I would go. Takes a little more, less nervousness and more, that's the politically right way to say it. Gumption, there you go, to accomplish it, but it can be much higher yield. So, any other questions? Great.
That's it? No more questions?
I can throw this back up here so you guys can look at it. Gimme, gimme!
Those last years, like what would they be used for? Would be used for the silicon discs or?
No, I mean,
No, not silicon, glass.
yeah. So I mean, like, I mean, I had some discussions with a watchmaker early on, and basically what he said was, you know, the general trend in high-end watches is to provide a lot of fancy, you know, intricate engineering at the face. So when people look at a watch, it's not just to tell time, it's like, look at how intricate this watch is on the inside. But he said, you know, the problem with that is you get that first layer of gears, and you can't see past them. So, you know, 4 years later, I put together some designs on some glass ones. You can see through them. I have no idea. You know, in general, you know, metals are 4 or 5 times stronger than glass. You know, Young's modulus wise, maybe more. it's all at those sizes. You have different degrees of force to realize. You know, at those sizes, when you look at like, you know, gee, if we all had, you know, what's the difference between a metal bumper and a glass bumper on your vehicle? It's huge, right? You would never want to have a glass bumper, but you know, just doesn't make sense. But at those forces, at those sizes, it's a different kind of force. It's a different regime, and it doesn't really. There's a lot more leniency in materials, so I would suspect it would hold up okay. Still looking for. I have a solution who's looking for a problem. At least on that part.
Is durability a big issue with the glass components that you make?
Yeah, I mean, at the end of the day, mechanical reliability. I mean, think about your phones. How many times you pick them up and you watch a movie or you download a big document and it gets hot? I mean, it's 4 or 5 times a day. You know, so what will happen is inside your phone, all of the electronics will expand and contract, just like rocks do on the mountains in summertime and wintertime. And they expand and contract hundreds of times a month, maybe even thousands of times a month. And in that situation, you don't want anything like microfractures to form. You know, the last thing you want is 2 little holes next to each other and a crack between them. So mechanical reliability is important. It's just how you process it without breaking it. I mean, that's, you know, the nice thing is once you get a handle on it, it's not that bad. But people go glass electronics, and their immediate thought is to kind of freak out. But we've seen a lot more adoption recently, specifically last year. Tremendous amount of adoption last year.
And can I get this correct? Like, this is your idea, and it's your company, all of this stuff.
That's correct.
You're looking for janitors at the moment?
It's funny you should ask. We are looking for some people. We're looking at expanding in the next couple of months. So, you got a business card, a little piece of paper with your name and number on it. So,
Who on that list are you looking for?
you know, right now our big thing is looking for an industrial engineer. You know, at the end of the day, I probably do 5, 6 unique jobs a week, sometimes more, and each one has, you know, different tolerances and different specifications. You know, one customer's through hole has to be 70 microns plus or minus 10%. This customer's is 70 plus or minus 6%. This guy's is 6 microns. I'm doing some projects along those lines. Managing all that. What's the workflow? That's a challenge, so that's kind of the guy that we're looking at. I don't even know if industrial engineer, yeah, number 14. So.
In terms of a startup company, did you bring investors in, or how did you? Are you like financially secure through this whole ride, or?
No.
Are the majority of the company still?
Yeah, I mean, so the company has been solvent the whole time. As the business owner, when there's hard times, you're the first pay cut. I mean, because at the end of the day, as an engineer, as an entrepreneur, it's not just your family that has to get fed, it's all of your employees' families. And you know, when you bring on an employee and you might have 10 people in the business, you know, you may not want to be their friend, but you are. And that comes, you may not want to be simply because you don't want to get that transparency into their life. But you know, you learn about their grandkids or whatever by default. And so, yeah, so you know, like I said, when times are tough at the company, you're the first to get the pay cut. And guess what? You get to work not only hard, but twice as hard, bring in more business. I was fortunate on my side. When I was at Sandia, I developed some technology to do. They were glass pillars. They were small enough to go into the past the first couple layers of your skin, but not long enough to touch your nerves. And we would metalize them, and we would allow us to do redox measurements inside the body. So the goal at that point was to do glucose detection. So there was a process called the Clark electrode, developed in 1970 by some guy named Clark. And it was just to determine how many how much glucose do you have? And it's the dominant method for determining for diabetics. But diabetics have to poke their skin and it hurts, and diabetics at you know, in the late 90s were saying kind of like, I'm not going to do it anymore. So we developed these little microneedles. I ended up winning a couple of awards for it. In 2007, I won an R&D 100 award, which is one of the Oscars for inventions. And so I looked at commercializing it, because I was, you know, at the time I was bringing all these kinds of these large industrial partners in from, you know, from the, you know, the private businesses into Sandia, and I said, well, I can do this on my own. So I left and I started the business on that model. And then that was the same year that Lehman Brothers fell. In fact, Lehman Brothers fell like 2 months before I left. And then, as you guys know, all hell broke loose in the capital market space. VC money dried up very quickly. And from my perspective of going for an FDA qualified product, I had to think real quickly, what else could I innovate? What else could I invent to keep my job? And that's when I came up with the glass. So, gotta do what you gotta do. Well, it wasn't that easy. It was a lot of late nights, but so. But yeah, I mean, that's kind of how I got my start. I mean, the people I brought on were good people. You know, stuck to their word, and you know, we're still in business. You know, today. So.
Do you work out of New Mexico, or in terms of like long term, do you have plans to?
Absolutely.
Operate?
Yeah. Yeah. No, I like it here. I mean, I've been here for 15 years. I mean, I'm still just visiting, but I don't think I'll be leaving for a while. So.
So, how many employees do you have?
Right now we have, I think we're up to 13 employees. We're still kind of small and lean. Most of our work is, I mean, it's pretty efficient, you know, what we can accomplish. So we don't really need a whole lot of employees, although, as I mentioned, we're looking to expand because the work's getting greater.
So the glass was to take the place of the dielectric and get like the liquid, I guess, dielectric. They use sometimes on the PC boards and stuff like that.
Yeah, it's really just replacing PCBs, so printed circuit boards. It's replacing those. You know, I mean, back when I was in college, I'm going to date myself, you know, you had the towers, laptops weren't even barely used. We had these big towers, and each one had these big, huge, you know, green board cards, you know. Those things nowadays are about that big. And they want to go smaller, and that's what we allow them to do. I mean, it's kind of funny. I mean, in your cell phone, if you ever break it and look inside of it, there's all kinds of, you know, flexible printed circuit boards nowadays. But there's a lot of circuit boards. They may not be green anymore. They may be, you know, some other variant of FR4, but they are still basically laminated pieces. It's a glass woven fiber that's kind of, yeah. They take the glass woven fiber and then they surround it by a resin, like a resinoid, and so that's why they call it a laminate, because they can take multiple pieces of that and stack them together, and they can make those pretty small and pretty thin nowadays.
So which happens first? Does someone approach you and say, hey, I'd like to make smaller ICs now? Do you have a substrate that can accommodate that? Or do you just keep making it smaller and say this is?
Well, it's a little bit of both. I mean, you make the watch gears to get the guy to ask you, why would you use this? I mean, because it piques their interest, and it's something that they can physically relate to. Like, you know, again, holes in glass doesn't really mean a lot, but like a watch gear, you know, I've done, you know, my company logo in there, and it's, you know, 3 different sizes are like small, medium, large, and they can see only one of those. You know, it can relate to that because it's more tangible, but so there's a little bit of that, but I think for the most part, it's, you know, getting the word out. You know, we started this business in 2000 and technically started in 2007. I left right around 2008. We started off as a life science business. You know, after the micropillars went into glass from microfluidics. Followed that for a couple years, but really got into glass interposers, or not really interposers, but glass PCB kind of replacements. Really back in about 2009, we were one of the first companies to ever kind of throw this out there, which is hard because, as I mentioned earlier, 2013 was kind of really the first big year and tick up of interest we saw. I mean by big tick up is you don't have the early adopters. You have the major players in industry talking to you. It's much different when you got a guy that's got maybe 100 employees talking to you versus a guy that might have 100,000 employees. And those 100,000 employee companies really weren't talking to us until last year, or at the level they are right now. So 2009, 2010, it was kind of scrimp and save and get by with the 100 employee guy. So it's a long haul, it's a long process. That's the downside. The good side, you get in early, you get a great IP portfolio. We have great positioning. We were in this game, years before anyone else was. So. All right. Anything else? Great. Oh.
I don't know if it's part of your trademark, but so what exactly is your glass composition? Or I don't know if I understand.
No, I mean, there's published patents on it. You can read it, but I'm the only guy that knows what that is. I mean, that's the at the end of the day, that's where the money is. So we try and keep that confidential.
It's a secret sauce.
Yeah.
I figured, but I'm curious.
The name, where'd you come up with it?
Well, as I was telling Matt before, I mean, what the biggest driver of coming up with a business name is the website available. We came up with a lot of cool names, but they existed in Australia or they existed in Belgium or whatever. In which case then we could not get that exact name. So 3D Glass Solutions was a name that was available. So we stuck with it. Likewise, before that, my previous company name, Life Bioscience, was also one that we found the same way. So. Apex, I could tell you that Apex stands for, the pinnacle, the upper echelon, the highest point on any, endeavor, such as a mountain. But really, the truth is, when I was making the composition of the glass, I had a jacket that had Apex written right here. I liked it. So it has a registered trademark. So it was also available. All right.
You guys good? Okay. Thank you.
Yeah.
Thank you.
Yeah, you bet.